Great. Hi, everyone. So welcome to the afternoon session of the third day. So we're very happy to have Dmitri Pavlov from Texas Tech University, who is going to tell us about the geometric cobordism hypothesis. Dmitri?
Yeah, thanks for inviting me here and giving this opportunity to speak. And also thanks for the organizers for making this possible and for putting all the effort in organizing this wonderful workshop. So what I'm going to talk about today is a joint work with Daniel Grady from Wichita State University in Kansas. Two papers are already on arXiv, and more are on the way, so there will be several more papers in this series. And for those of you who, like me, sometimes are lost when you have too many slides and you want to go back to the previous slides, I put my slides online, and this easy to remember URL. If you feel like you want to go back one or two slides, you can always open them on your laptop or your phone. Please do so if you are, because that's something I often like to do myself. All right. Let me extremely briefly say a few words about the origins of this formalism of functorial field theory. So it all originated in physics, where you would want to construct quantum field theories by integrating over infinite dimensional spaces, like maybe mapping spaces between some kind of manifolds. And the name of Feynman's name should probably be mentioned as the originator. And eventually the construction got significantly generalized. And somewhere in mid-80s, Ed Witten was giving a talk in a physics seminar, I believe, where he was explaining the axiomatic properties of path integrals, what came to be known as path integrals. And Graham Siegel, who was in the audience, remarked that this looks like a symmetric monoidal functor from the category of conformal bordisms to Hilbert spaces. And that's basically how the subject was born. Of course, you probably know that almost immediately most researchers started to study topological theories, where the geometric structure in bordisms is of a simple type, like orientation or maybe a spin structure or framing. And the majority of papers have been going in that direction. But the original goal, so to say, to axiomatize what the constructions that physicists are doing, it still remained. So a lot of work has been done in the direction of topological field theories, like, and I listed some references and some names here, but still the original sort of idea was still there, and not much progress was made on that. So you can see, some work has, like, very significant progress has been done on the classification of topological field theories, but in terms of sort of field theories that depend on the geometric structure on your bordism, so far very few examples have been constructed. In dimension 2, for non-fully extended field theories, we have like a couple of examples known, and that's pretty much the best we could do so far. All right, so today I would like to talk about sort of a general classification result that allows you to construct non-topological field theories in arbitrary dimensions. Well, and maybe I should say a word about history of the terminology. I think it was Urs actually who proposed the name functorial field theory like about 15 years ago, right? Yeah, so it's before that we only had like specific names like conformal field theory maybe, or Euclidean field theory, but not a generic, fully encompassing name. So it's nice to be like a nice little fact for you. Okay, so since most people in the audience have at least some idea what a topological field theory is, let me instead of trying to give you a complete definition, let me try to emphasize some special features of the geometric Bordism category that will be important in the theorem that we'll explain later. So I think there are about 4 such features that we should consider here. The first one is that the functorial field series will be functors from the appropriate category of Bordisms to the appropriate category, target category. And Bordisms will have corners of arbitrary codimension. So you start at points. Then one morphisms will be intervals between points, 2 morphisms will be surfaces between intervals, and so on up to dimension D, where you have D-dimensional Bordisms with corners of arbitrary codimension. So that's known sometimes as fully extended functorial field theory, or some people would just say local field theory, and we'll explain in a second where the name local comes from. Okay, so that's a feature that may be also familiar from topological field theory. Some work has been done by Chris Chammer-Priest and Kevin Costello on the classification of fully extended topological field theories, and in fact, we have seen some talks where this was mentioned. Another feature is that we above dimension D, we don't stop at dimension D. We also have morphisms above dimension D, and these morphisms will encode if you want, the homotopy type of the group of diffeomorphisms of your Bordism in dimension D. And again, this feature has been known for a while. It's already present in Kevin Costello's work on 2-dimensional topological field series. And in fact, it helps you to work with targets such as chain complexes. So for chain complexes, you really don't want your field series to be just ordinary strict functors. You might want some the associativity relation to be satisfied maybe only up to some homotopy coherence. And in fact, in physics, the BV-BRST formalism is sort of uses pretty much, for the BV-BRST formalism, this is pretty much a requirement that you have such targets with which are chain complexes, or maybe something made out of chain complexes. Okay, so the first 2 features are already present in some form in topological field series, and the last 2 are really specific to the non-topological case. So all Bordisms that we are going to consider will be equipped with a geometric structure. And a geometric structure in our setting is an extremely general notion. We'll give a precise definition maybe on in a couple of slides. But for now, let me just mention a few examples. You can put Riemannian or Lorentzian metrics on your Bordisms, symplectic structures or conformal structures. You can equip your manifolds with principal G bundles with connection, bundle gerbs with connection. So anything that can be defined locally on a manifold is a fair game here. And finally, the smoothness property tells you that the value of your field theory depends smoothly on your Bordism. So for example, if your Riemannian metric on your Bordism changes smoothly, then the corresponding values of your field theory also have to change smoothly. So we'll explore more of these properties in the following slides. So, all right. Any questions so far? All right, let's move on. So here's a picture that sort of illustrates how Bordisms are composed in dimension 2. The dashed lines separate various Bordisms. You can see that Bordisms have a boundary and corners. Corners have codimension 2. Now, if you imagine that each of those pieces is equipped, for example, with a Riemannian metric, if you think about this carefully, you may wonder how two Riemannian metrics, how two Riemannian manifolds can be glued along their common boundary, which is actually not a trivial thing because, for example, if the curvatures don't match at the boundaries, and there is no way to glue. So the solution that has been known, at least since the work of Stolz and Teichner, is to equip all Bordisms with a d-dimensional germ of a geometric structure. So in addition to the compact Bordism itself, it has a tiny neighborhood. And on this tiny neighborhood, you also have a geometric structure. Having those little germs, or colors if you prefer, around the boundary allows you to compose Bordisms by gluing them over the little neighborhood of the common boundary. Which kind of naturally leads us to our definition of a geometric structure. So you can see that all geometric structures live in the top dimension, in dimension D, where D is how many categorical layers you want to have. So, so this sort of naturally leads us to this definition of a geometric structure. A geometric structure will be defined as a sheaf on a second side. What is a side? Well, in the first approximation, you can think of it as the side of d-dimensional manifolds with morphisms being open embeddings. And covering families are given by open covers. That's not quite right in a sense that it doesn't allow you to talk about the smoothness property, the fact that a field theory must map a smoothly changing family of Bordisms to a smooth family of values. So there's this little complication you have to add, that all d-dimensional manifolds have to come in families. So an object in your psych is not just a D manifold, it's a smooth family of D manifolds. And morphisms are not just open embeddings, they are fiber-wise open embeddings. So you have a map between base spaces, and for each point in the base space, you have a map between the corresponding fibers, and this map has to be an open embedding. So it is this additional sort of feature that precisely allows you to talk about smoothness of field theories. All right. Let's see. Yeah, so now a geometric structure is just a simplicial pre-sheaf, so a contravariant functor from this side to simplicial sets. Just to give you a simple example, pick an object in the site, so a family of d-dimensional manifolds over a parameter space U. So every fiber of this map from T to U has dimension D. And you assign to such an object, you assign it to the set of fiber-wise Riemannian metrics on this family of d-dimensional manifolds. If you have a fiber-wise open embedding, then you can take a fiber-wise Riemannian metric on such a family and restrict it along this fiber-wise open embedding. So this type of construction produces for you a pre-sheaf of sets on this side. All right, so there are many, many more examples, and I just listed some of those in the slide, like Riemannian-Lorentzian metrics, possibly with restrictions on curvature, conformal, complex, symplectic structures, foliations. Some of the more important examples include the sigma model. So the sigma model would have as a geometric structure a smooth map from your bordism to a fixed Target manifold M.
Can I ask a quick
Yeah.
question? In your previous slide, your geometric structures give you a simplicial presheaf. So in your example, are you thinking of Riemannian metrics as a simplicial set? You're thinking
Yeah,
of all
so
your...
the Riemannian metrics form a discrete set, and a discrete set can be promoted to a simplicial set just by producing a discrete simplicial set.
So
yeah.
where's the topology of metrics, Riemannian metrics?
It's not in this example. So in this example, the smoothness is accounted for in the direction of U. So when you say, take a non-trivial U, and you can have a non-trivial smooth family of Riemannian metrics with respect to U. As you go around U, your metric will change smoothly. And that's how the topology is accounted for. It's accounted for by the U variable and not by the simplicial set.
I see.
So the simplicial set is responsible not for smoothness, it's responsible for the stuff like gauge automorphisms and higher gauge automorphisms. Smoothness is accounted for by the Cartesian, so the Cartesian space U.
So the fiber is just in this case, it's just discrete as a set of metrics.
Yeah, so the set, yeah, that's why I said it's a set of all Riemannian metrics. Yeah. Yeah.
Okay, thank you.
Right, more questions? All right. Yeah, so the sigma model can be encoded, and given the level of generality that we use to formulate our setup, even stuff like maps to orbifolds or maybe higher scats is perfectly legitimate. Of course, topological structures are still present, like orientations, framings, spin structures, string structures, and differential geometric structures like differential forms are also, of course, available to you. Here's one more example. How do we encode gauge fields in the setup? You would say, so if you have a d-dimensional manifold M, you would send it to the nerve of the groupoid whose objects are principal G bundles on, sorry, it's T, yeah, no, it's the same object T over U. I should have said, send a family of D manifolds T over U. So you send such an object to principal G bundles on the total space, and you have a fiber-wise connection. So on each fiber, you have a connection, and as you move around U, your connection has to change smoothly. So we know, for example, a connection, well, you can say, for example, is a subbundle of horizontal spaces, and we know what it means for such a subbundle to be smooth. All right. And again, like we have a whole bunch of variations.
Can I just ask a question? So here you mentioned, well, in the previous slide you mentioned sigma models with target space and orbifold.
Yeah.
So what about like if I wanted to do like gauge theory, but where the world volume is an orbifold, not a target space, but with the world volume?
World volume is an orbifold. That's a good question. Well, it depends on where the orbifold structure comes from, I guess. If it just modeled by some group action, right, that you can encode this by just mapping your Bordism to the classified space, right? Well, it's really a question of where the orbifold structure comes from, I guess. I mean, it's well, maybe if our question is, what is an orbifold Bordism category in the first place? I'm not
sure. I suppose so. Yeah.
Well, I have several answers, but maybe we can discuss after the talk.
Sure. Yeah. Thank you very much.
It's a long topic, I would say.
Thank you.
Yeah. All right. Yeah. So again, a whole bunch of higher gauge fields coming from physics, like bungle gerbs of various degrees, or spin C structure, 5-brane, 9-brane structures, differential K-series fields, which in physics, or at least a lot of mathematicians would say are the same as Ramon fields. And that's also covered. And this last example, by the way, demonstrates why you need this level of generality that I used, like simplicial sets. Do you really need simplicial sets? And the answer is yes, if you want to encode stuff like Ramon fields, which form an actual infinity groupoid and not just, say, an n groupoid for some n, right? So it's not really truncated at any point. So here, for example, you need the full generality of simplicial presheaves. So everything we do in this definition, every single generalization was motivated by some application coming from physics, and it's not generality for the sake of generality. Okay, so I think that's it for geometric structures. Any questions about geometric structures? All right. Let me now proceed to the main theorem. So let me first talk about the ingredients for the main theorem. So first, you would fix a dimension D and a d-dimensional geometric structure S, which, as we have previously seen, is a simplicial presheaf on this side fmd. You also fix some category of values, or more precisely what we call a smooth symmetric monoidal infinity D category of values. If you don't know what this means, just think of the usual symmetric monoidal category where you also are allowed to have higher morphisms, like 2 morphisms and 3 morphisms. And smooth just means you have a sheaf on the side of smooth manifolds. The smooth symmetric monoidal infinity D categories are just sheaves of symmetric monoidal infinity D categories on the side of smooth manifolds. Okay, so given this input data, we can construct, first of all, the category, again, smooth symmetric monoidal infinity D category of Bordisms with such a geometric structure. And I'm sorry, I cannot really discuss the definition in any considerable detail. In fact, there are whole papers out there which are devoted just to writing down some definition of the Bordism category, and some of those papers are pretty long, actually. So, but I will be happy to talk about the details after the talk. But the essential features were already described. You have Bordisms of dimension from 0 to D, and Bordisms come in smooth families, which means the field theory must map smooth families to smooth families. Bordisms have a geometric structure as described on the previous slides. Okay, so with those definitions in place, now we can define a d-dimensional functorial field theory with geometric structure S and with V as its category of values, as a smooth symmetric monoidal infinity D functor from the Bordism category to V. So this is precisely the type of definition we are all used to in topological field series. Of course, here there are many bells and whistles that had to be added. But again, everything we added to the definition was motivated by some concrete example from physics, and not really just added randomly because we felt like generalizing. And even more, in addition to defining a specific field theory, let me also point out that this formalism is capable of talking about the whole space. In this case, I'm talking about the whole simplicial set of field theories, which is a philosophy advocated by Stolz and Teichner, that you should be looking maybe at whole spaces of field theories, and these will be providing for you models for various cohomology theories. And in our formalism, it's very easy to define the space. It's simply the derived mapping space in the appropriate model structure. And you can even further refine this to a derived internal Hom, so let me not talk about that. So let's keep it as simple as possible. Yeah?
Why is this a space? I mean, don't you need some sort of dualizability to see it's a space?
Dualizability will show up a bit later when we when we state the actual theorem. So you don't need dualizability to actually define field theories, right? It's the fact that you land in dualizable objects is something you can prove by sort of looking at Bordisms and how they interact. So it's a property of the Bordism category that functors out of it magically land in dualizable objects.
But you're claiming you're mapping an infinity D category to another infinity D category, and such functors actually end up giving you an infinity. It give you a topological space as opposed to another infinity D category.
Well, the full notion would be the derived internal Hom, which would give you a smooth infinity D category. Yeah.
And so how do you get this space out of it? You just...
if you discard the non-invertible morphisms,
I see.
You get precisely a simplicial set or a sheaf of simplicial sets. Yeah.
So that's different, right? In the Cobordism hypothesis, you don't need to discard anything.
Well, here you also actually don't need to discard it. It's you can prove that in the setting we will examine, you can prove that natural transformations between field theories are automatically invertible. But again, this is a little argument you have to make. And once you make it, yes, it will land in invertible morphisms. So although it may seem like you get an infinity D category of functorial field series, in reality, you only get an infinity groupoid, a simplicial set.
I see.
Yeah. Yeah.
When you define your Bordism category, do you have to take geometric structure and restrict it to codimension 1, 2, 3? Or
No, you never restrict to any codimensions, because remember, all K morphisms, which are look like K-dimensional Bordisms, they secretly, or maybe not so secretly, have a D-dimensional germ around them. And it is on this D-dimensional germ that the geometric structure actually lives. So there is no geometric structure on genuine K-dimensional manifolds if K is less than D.
Okay, and you never have to restrict it kind of to
That's right. So you only restrict along open embeddings. So if you have a structure, say on D Bordism, you can restrict to the source. The source looks like the germ of a D minus 1 dimensional manifold, but the germ itself has dimension D. Yeah. Okay, more questions? All right, so with those definitions, let me sort of mention somewhat ahistorically, but a couple of conjectures formulated in the early 90s. The first one states, the first one originates around 1992 in the work of Frege and Lawrence, who observed that who made this observation that we probably want to extend our Bordism category down to points if we are to get, well, I formulated by saying that functorial field series form an infinity sheaf with respect to the geometric structure. So what you should be thinking about here is imagine your Bordism maps to some fixed target manifold, which like a sigma model, and you cover your target manifold with an open cover. And the question is, if you know the value of your field theory on Bordisms that factor through one of the elements of the open cover, can you recover the value of your field theory on an arbitrary Bordism with an arbitrary smooth map to the target manifold? And if you contemplate this for a second, you say, okay, maybe I'll try to cut my Bordism, my arbitrary Bordism, into many, many, many tiny pieces so that each piece is factored through some element of the open cover. And this is possible as long as you can cut along manifolds of arbitrary codimension. So as long as you allow manifolds with corners of arbitrary codimension, it is very obvious you can like chop your manifold into tiny, tiny fragments which all will factor through arbitrarily small open subsets. So with this sort of heuristic argument, you can say, oh yeah, okay, then in that case, if we allow to go down to points, we expect that the functorial field series on an arbitrary target can be reconstructed from functorial field series given by its restriction to some open cover. And that's sort of intuitive explanation for this sheaf property that if you fix a dimension and a category of values, then the simplicial set of functorial field series satisfies a descent, a gluing property with respect to open covers of your geometric structure. And there is one more conjecture, which is the actual Cobordism hypothesis that was formulated by Baez-Golan in 1995 and later improved by Hopkins and Lurie in 2008. And of course, we have to generalize it even further to geometric structures. So that one actually allows you to compute the space as a second mapping space. So our map on the right side is simply the derived mapping simplicial set. Or if you prefer infinity categories, you can say it's just a mapping space in infinity categories from S to invertible part of the fully dualizable objects in V, which you turn into a simplicial pre-sheaf on the side FMD by providing it with a certain action of the orthogonal group, which I will discuss on the next slide. So you can see, by the way, that the second statement is strictly stronger than the first statement because the right side in the second statement is clearly a sheaf with respect to S, right? Mapping S to some fixed target clearly satisfies a gluing property with respect to open covers of S. So you can probably guess that to prove the second statement, you will somehow have to prove the first statement also, and that's precisely how the two papers work. The first paper proves the first conjecture, and then the second paper exploits this result to prove the second conjecture. Okay. So here's a precise statement. So the first part says the functorial field series satisfy a gluing property. And we can express it in a fairly elegant way by saying the functor that sends a geometric structure S to the smooth symmetric monoidal infinity D category of Bordisms with this geometric structure is a left adjoint functor. And what is the practical consequence of this statement? The practical consequence is that the left side, which is smooth symmetric monoidal functors from the category of Cobordisms to a fixed target, can be computed as by a junction property. You can move this functor board D to the right side, where it is replaced by its right adjoint, which here is depicted as V cross D. So you can compute the space of functorial field series on the left side as the mapping space on the right side. Unfortunately, if you stop here, it's really not enough to do anything about functorial field series, because the way this right adjoint works, its value, so the right adjoint V cross D is a simplicial presheaf on FEM-D, and its value on some family of D-dimensional manifolds is simply the space, the simplicial set of functorial field series with such a representable geometric structure. So that's difficult to compute. So it almost seems like the first statement reduces maybe something difficult to compute to something else that is difficult to compute. And this is precisely where the second part comes in, which says that if you, this right adjoint can actually be computed as the, take the invertible part of the fully realizable objects in V and discard the non-invertible morphisms, which, so what remains is just infinity groupoid. That's if you want a simplicial set. And so part 2 says, yeah, that's precisely the value of your right adjoint on some representable presheaf in your, on some object in your site. So this allows you to compute the right adjoint in a practical in sort of a very practical way, and we'll see an explicit example in a second. And so when taken together, the two parts allow you to very efficiently compute spaces of functorial field series that previously were completely inaccessible to practical computations. Okay, so any questions about the statement? Yeah.
Which equalities here are definitions? Which equalities are results?
Yeah, so let's see. So so this arrow is a weak equivalence. That's a non-trivial result.
Yeah, I'm talking about the equalities. There are 1, 2, 3 equalities.
Yeah, all the equalities are tautological. So this is just this equality is basically just a definition of what it means to be V cross D. What it means to be the right adjoint. If you think about how the right adjoint works, imagine S here is a representable presheaf, right? Then by the Uniacke lemma, maps from a representable presheaf to some right adjoint should be the same as maps from the left adjoint applied to this representable presheaf to the original argument. So, and that's precisely what is written here, that the right adjoint evaluated on some representable is precisely a functorial field series with this geometric structure.
So that second line, the equalities follow if you assume the theorem written above it, right? If you assume that theorem, then the next line follows. Not part 2, I'm just talking about part 1. The line right above it is a theorem, right above it. Yeah, that's a theorem, and assuming that theorem, the next line follows as a tautology. That's what you're saying.
Yeah.
Okay. So the equalities are not tautological until you assume part 1.
Okay, you can say this, but in reality, what we do is we say, let's define this side as this expression, and then we prove the theorem, and then this equality becomes also tautologically true.
But then, you see, if you define it, how do you know you have a space?
Okay, yeah, so strictly speaking, yes. So I should have meant, if you want to be precise, you would take the invertible part here.
Okay.
Yes.
Yeah, okay.
Yeah.
Thank you.
Okay, more questions? Okay, let's move on to computing maybe. Yeah, so I just get some applications here, but I don't have any time to talk in any detail. I think Gan Grady will talk about the Frege-Hopkins conjecture. So, I will actually discuss one of the next application, which is construction of pre-quantum functorial field series right away. Okay, so the general recipe, if you were to apply the geometric Cobordism hypothesis, is basically you follow the structure of the main theorem, and in the first step, you will compute this right adjoint. And notice this is something you only need to do once for every possible choice of the category of values. And since there's only like a fairly limited number of such choices, in many situations, you won't even need to do step 1. And in step 2, you would use the computation in step 1 and compute the derived mapping space, which will tell you what functorial field series are in your case. Okay, so how do you do both steps? For the first step, you would try to guess some candidate for what the right adjoint is, and try to define a map to the actual right adjoint, which is defined as functorial field series, or rather their invertible part. And then you would apply the geometric Cobordism hypothesis to say that this map here is a weak equivalence if this composition is a weak equivalence. And when you look at this composition, both the left side, which is something you guessed yourself, and the right side, which is just the invertible part of the value category, both sides make no use of field series. So the field series were in the middle here, but once you took the composition, you can forget about field series and just prove what in practice amounts to a very simple statement about a weak equivalence of some simple simplicial presheaves. Roughly speaking, kind of like a Gram theorem maybe, or something along those lines. So this is actually not difficult. And in step 2, you would maybe deploy known techniques for computing the spaces of maps between simplicial presheaves. It kind of looks like computations in differential cohomology, roughly speaking. So let's look at now at a very concrete example of the pre-quantum Chern-Simons theory. So the input data in our case will be a Lie group G. The geometric structure will be a fiber-wise principal G bundles with connection. The category of values will be a particularly simple category. It's the threefold de-looping of the Lie group U1. So you think of this category as having a single morphism below dimension 3, and 3 morphisms are elements of U1. Now, that's not quite true, because once you sheafify, you will also see non-trivial morphisms below dimension 3, which will be given by bundle gerbs. But in the first approximation, it roughly goes like this. And the output data should be a fully extended, smooth, non-topological, 3-dimensional functorial field theory with the indicated geometric structure. And of course, to a closed 3-manifold, it should assign the Chern-Simons action over this manifold. So the 3 manifolds are equipped with a principal G bundle with connection. I wrote down what is supposed to assign to higher codimension manifolds, the pre-quantum line bundle, the West-Seminger weakened gerb, and finally, to the point here, are supposed to assign the Chern-Simons true gerb. And as you can see, there's a lot of structure being packed here, so it's not exactly trivial. If you were to do this by hand, it would be very painful to even write down all of this and verify carefully, and the difficult, which probably explains why it hasn't been done yet. Okay, so let's very briefly see how those steps can be performed in a concrete fashion. So first, you would compute the right adjoint for this very simple target. And as the recipe dictates, you would first guess some candidate for the answer. And if you ever work with differential cohomology, it will be natural for you to get the fiberwise Gallien complex, which is just the Gram complex, but instead of differential zero forms, you have smooth U1 Wallich functions. The second step tells you to guess a map from your previous guess of what the answer should be to the actual right adjoint. So it's supposed to take, maybe on a sort of, roughly speaking, it's supposed to take a fiberwise differential 3 form and produce from it a framed functorial field theory. And what this theory is, it's a very simple theory. It has no non-trivial topology in it. It literally just integrates a differential form omega over some 3-dimensional Cobordism and takes the exponent of the resulting, I should have probably said exponent of I times this number. Yeah, so it produces an element of U1 given by exponent of I times this integral. So again, it's very easy to write down such a field theory. You don't have to do any non-trivial verifications. You just integrate differential forms, and everything else is essentially tautological. So there are none of the usual difficulties associated with construction of field theories. For framed field theories, is all like very primitive. And finally, the last step dictates that you look at the composition, where you would take the right adjoint, and, which is the space of framed functorial field series, and evaluate it at the point, which in our case simply gives you these, the space of what I call the fiberwise constant functions with values in U1. And then the whole composition will be a weak equivalence by the Poincaré lemma, which says that this chain complex here is exact except for the very top degree, where the kernel is given by, in our case, fiberwise constant functions with values in U1. And you may ask, well, what happens in the bottom term? We don't really have closed forms here. Why am I claiming that it is exact also in this term? But recall that everything is done in families of over 3 manifolds. So these are fiberwise forms on smooth families of 3-dimensional manifolds. And on a 3-dimensional manifold, every 3 form is closed because it's a 3-dimensional manifold. So really, also in this term, you are closed, so the whole chain complex just boils down to the kernel of this differential here. So that wasn't too difficult, I hope, and it's something you can do, and it doesn't require any immense efforts to prove. And in the final step, you apply what you computed in step 1. Let's see how much time. Oops. Yeah, so that's the last slide. So you take what you computed in the first step and substitute it in the second part. And to construct an actual field theory, you just need to construct a map of simplicial presheaves from being obligee to your candidate for to the value of the right adjoint, which was computed as maybe fiberwise constant functions, or quasi-isomorphic model, the fiberwise Gallien complex. And this is actually has already been done in some form by Berlinstein, McLaughlin, and in sort of more explicit form by and Domenico, Hisham, and Urs, all of whom are present here actually in this room. Yeah. So yeah, it's not exactly the same. You need to do like a little bit of adjustment because the site is slightly different from the usual site of smooth manifolds, but everything works pretty much exactly the same fashion and gives you a specific map, which we now see actually gives rise to a full-fledged functorial field theory. And of course, the story doesn't stop here. You can actually compute the whole mapping space fairly easily. It's just some variant of differential cohomology. So you can compute all possible sort of field theories of the Chern-Simons type, or at least of the same form. And again, this is something, this will be a subject of maybe one of the forthcoming papers. All right, I think that's, sorry for going over time a bit, but I think that's a perfectly good time to stop. Here is a slide for you to enjoy, just if you have any questions how to do quantization, but I'm not going to talk about it right now. Yeah, thank you.
Great, thank you very much, Dmitri. Further questions for Dmitri?
So you could actually model conformal field theories.
Yeah.
Too. So okay, so here's a random question, completely random. Can you see some sort of flow over here, some sort of RG flow or something like that? Because you'd expect flows in these kinds of theories to abut to conformal field theories.
Well, the RG flow is more like perturbative, right? Or
it could be, yeah, I mean, you're right. I mean, there's something to do with coupling constants, but still.
like, do we know how to define RG flow in a non-perturbative setting? Like,
Highlight the metric.
huh?
You probably have it. If you dilate the metric on a Riemannian Quordism, that's RG.
Oh, okay. So you just rescale the metric by a constant?
Yeah.
Oh, okay, yeah, no, yes. And in that case, the answer would probably be yes, yeah.
So you actually, okay, well, that's impressive. Then people should be excited.
Yeah, I am.
That's cool.
Yeah.
But then to see non-trivial renormalization group flows, you would have to perform the quantization, isn't it? Because in this initial step, it's just an action functional with a bit of co-dimension, whatever data, and there you don't see any renormalization.
Yeah, no, of course.
So there's probably some choices you have to do here in this quantization, which give you extra parameters to vary, and then you see kind of.
Yeah, and in principle,
effects.
yeah. I mean, that's something we would be looking at in one of the future papers, I hope. But yeah, you can see, in principle, you can now do quantization in this setup because at least the way quantization is traditionally interpreted in the language of functorial field series, you have a functorial field theory over X, which could be something like a target manifold for a sigma model or something similar. And you want to produce a functorial field theory over Y. Y could be something like a point in the simplest case, or maybe some simple geometric structure that does not contain the target manifold anymore. And then the left map should be sort of as integrating out, like integrating over infinite dimensional spaces of maps from bordisms to the target, which is of course extremely difficult to define, but the geometric cobordism hypothesis replaces the left map, which you don't know how to define, with the right map, which is just a map between certain derived mapping spaces of simplicial presheaves. And that's, in principle, quite accessible to concrete constructions. It doesn't necessarily even require you to write down any infinite dimensional integrals. So one of the future directions planned is to study quantization in this setting.
Excellent. Any other questions? Okay, yeah.
So on the right-hand side, when you say quantization, you just mean there might be a map like that?
right? Or do you have a prescription to actually?
Well, in dimension 1, you can actually easily write down a map and you recover the usual spin C geometric quantization, where you would, the geometric structure X would be maybe just a smooth manifold, which you assume to have maybe a geometric spin C structure. The top right corner will simply encode the spinor bundle as a one-dimensional field theory, which is simply the parallel transport of the spinor bundle. And then you can easily write down this right map, and you, in dimension 1, everything sort of becomes more or less simple to compute, and you will simply recover the Dirac operator. In the bottom right corner, you will see a one-dimensional Riemannian field theory. So what is a one-dimensional Riemannian field theory? Is a choice of an object in V together with a one-parameter group of automorphisms. What is the object? The object is just the smooth sections of the spinor bundle. And what is the one-parameter group? It's the exponent of T times the Dirac operator. So that's just the usual picture of quantization, if you want, the Feynman-Katz formula, which sort of connects it to the physical intuition of integrating over infinite dimensional spaces. Yeah.
Okay, very good. Any other questions? Okay, if not, let's thank Dmitri again for the very nice talk. Thank you.